Suppose you have a new intervention, and we'll call that, well, the psychology series intervention. And let's say this is a cognitive training intervention, and you want to test its effects on some sort of clinical population, let's say people suffering from, I don't know, Alzheimer's disease, okay? And so you need to test this hypothesis, and therefore you would likely run a randomized control trial, because this is the gold standard for testing the effects of one variable onto the other one. And so you need to determine how many participants you need in order to detect a true effect, if there is an effect of this cognitive intervention on participants. For example, I don't know, IQ. So that's our dependent variable in participants with Alzheimer's disease. So let's say we've got our usual graph here, and we have our dependent variable, which is IQ, and then we have our pre and post as per usual, and I need to be randomly allocate participants in an experimental and a control condition in the at baseline, and then I want to give them the intervention, and then I'll measure their IQ here at baseline, and then again at post, and I want to detect some sort of change. Now, the question here becomes, well, how many participants do I need to randomly allocate into these two different conditions in order to detect a meaningful improvement in participants' IQ in participants with Alzheimer's disease? And I can run a power analysis, and this is now within between group design, by the way, and so we would be running a mixed model ANOVA. So the question is, I'm looking for a within change, so an improvement in the experimental to the relative to post, but I'm also looking for a between group, so a difference between the experimental or a greater improvement in the experimental relative to the control at post. Now I can run a power analysis in G-Power, and I can use a mixed model ANOVA in G-Power. I can input the option for a mixed model ANOVA, but I think that G-Power takes into account that you're also looking for a within group change as well as a between, which means that it will yield a smaller n. If, however, because we're mostly interested in, we are very much interested in the change at post, or sorry, the difference between the experimental and the control after the intervention, this now becomes a between group, this is the between group factor. And now we know that when you run a power analysis for a between group sort of design, the sample size will be larger, and that's because there's more individual variability between these two groups, because there are two different groups, which means that any effect will be masked. Some of that effect might be masked by the individual variability, whereas in a within group design you will need fewer participants because the participants are the same at pre and post in one condition, which means that the data set will correlate because they are the same people. You wouldn't expect someone to change by much if, let's say our intervention is 6 months. You wouldn't expect them to change that much as an individual, and therefore their scores will be affected a little bit by individual variability, and the rest of it by the effect of the intervention. Whereas between group design, the scores are affected a lot by error variance, as well as the effects of the intervention. So we might prefer to run a power analysis for a between group, which will give us a larger n. And therefore, if we have we're sufficiently powered to detect a between group difference at post-test, we'll definitely be sufficiently powered to detect a within group difference. So in order to run a power analysis, we need a number of parameters. So that's the effect size, that's power, and that's the alpha. The alpha is typically 0.05, that's easy enough. Then power is typically at 80. Now the tricky one is the effect size. Well, some students and even some researchers struggle to sort of determine or estimate what kind of effect size we're looking for, because well, we don't know what's the effect of our intervention on IQ in people with Alzheimer's disease. We don't know that. That's why we're running the study. But power analysis requires us to input this. So one way to kind of think about it in a way that could help us determine what kind of effect size to input is to think about it in terms of clinical relevance. So if I have the typical small, medium, and large effect size as given by Cohen, the question that I should be asking is, well, if I find that my intervention produces an effect size of 0.2 on the Cohen's d scale, is this effect size clinically relevant? Does it improve quality of life? If the answer is no, in other words, a 0.2 or small improvement or a 0.2 difference between these two groups is not that much, well, then it's not going to be clinically relevant, because it's not going to be beneficial to the patient or to the family in any way. So basically the question that we're asking is this: is the effect size deemed to be important to the patient, whether the effect or the change deemed to be important, whether the change is beneficial or harmful to the patient, not so much as to the clinician, but to the patient. If a small effect size is too small, then we may want to go for a medium effect size, which could give us clinical relevance and, in a sense, improved quality of life. And the question that we can typically ask, for example, in a memory disorder such as Alzheimer's disease, is that with a, for example, a small effect size, you may see an improvement in IQ scores, but if the patient still feels like they can't remember things, their family members also report that the patient still is very forgetful, then we need to think about using a larger effect size or trying to detect a larger effect size. If we do detect a medium effect size, then in that case, it is possible that the participant now, or the patient now, is able to remember things, and their quality of life has also improved. And so this is maybe how we can determine what sort of effect size we should be looking for. And it's very important because inputting an effect size of 0.2, wanting to detect an effect size of 0.2, will give us a much larger n compared to wanting to detect a medium effect size. So this can mean the difference between thousands of dollars or euros between trying to detect one of the two. So, but what does this 0.5 on the Cohen's d scale mean in terms of actual IQ points? How can we determine that? So that's quite simple. So let's say you've got your IQ scale here, and you've got the typical mean of 100 with a standard deviation of 15. This means that one standard deviation is equal to 15 points, and therefore a 0.5 on the Cohen's d scale is equal to 7.5 points, because this is half a standard deviation. Now let's say that well, our population is, has been diagnosed with Alzheimer's disease, and then they score a little bit lower now because they have Alzheimer's disease on the IQ scale. So they score half a standard deviation lower. So that's about what, 92.5? Is that 7 point? Oops, that's a 7. 92.5. So half a standard. So 100 minus 7.2 is 92.5. And so if we want to take participants from here back to here, we would like to be powered for detecting half a standard deviation. And that's what we were looking for here. Now, if this change from 92.5 points back to 100 is deemed to be clinically relevant, as well as improving quality of life, which, by the way, you should have a measure for quality of life. You can't just say that because it's clinically relevant, then it improves quality of life. I'm just saying this for purposes of illustrating what I mean. So if this improvement is deemed to be clinically relevant, then this is what we want to power our study for. And so we will be putting 0.5 here. Now I'll show you a couple of things with the power analysis as well. So what we're going to do is we're going to try to power our study to be able to detect a difference between the two groups at post-intervention, and therefore we need to run an independent sample t-test. So we'll choose this here. We've already got the t-test family. 2 because we don't know in which direction we're going to go. It could IQ could decline as well. So as I said, we have our effect size of 0.5, which was the difference of 7.5 points, power at 80, alpha at 5, and our allocation ratio, that's 1:1. And so now we have 128 participants and 64 per group. So in the experimental, we'll have, what was it, 64, and in the control as well, 64, 100, and ANOVA 128. Okay, so this is not the end, however, so, because we need to have a more precise sample size. This is just a theoretical sample size, and the reason is because we also run in a within group design, which means that participants will drop out by the end of the, the study, especially if you've got a 6-month intervention. And therefore we need to estimate what our attrition rate is, which can range from, I don't know, 10 to 30 to 40 to 50, 60%. But in order for you to estimate how many participants will be dropping out by the time that the study finishes, that's tricky, and it differs from research question to research question, actually. But it is important that you don't lose participants, because if you are powered enough, sufficiently powered with 128 participants to detect a between group difference at post, if you lose participants, you will be underpowered. There are 2 ways that I know of to estimate what the attrition rate will be, so you can incorporate it in your final N. We can put that F for final. The first one is to look at previous literature. So if in your area of research, previous literature has found that in participants with Alzheimer's disease and intervention in randomized controlled trials, the attrition rate is, let's say, 30%, then you would include an additional 30% of participants on this number. But if you don't know what the attrition rate is, because no one has reported that before, researchers typically go for 20% more or less. So you would include another an additional 20% on top of this 128. So we can just very quickly calculate that. So it's 128 participants times 0.2, so that's 20%. So you need an additional 20 5.6 participants, so that'll, if you round that to 26, so 26 plus the previous sample size, now we are at 154 divided by two groups, that's 154 divided by 2, that's 77 participants per group. And so in the control group, in the experimental group, we will have 77 participants, and in the control group also 77 participants. So if we lose 20% of participants, we'll still retain this 128. So the final N will be 154 participants. So this is the end of it. I hope you enjoyed it. I hope you learned something, and see you next time.